Hi, welcome everyone. It's a great pleasure to introduce Dr. Alan Condron from University of Massachusetts in Amherst. He will speak on a very, very interesting and important topic on how cyclones in the North Atlantic disturb the ocean circulation and contribute to deep water formation and also transport of water across latitudes. And so Alan grew up in England and he did his bachelor's degree at the University of Wales. And then, but for his master's degree, he came to UMass in Amherst, where he did some work on paleoclimate. But then for his PhD, he went back to England and he wrote his thesis at the University of Sheffield. And then he did his postdoctoral work at Woodstow, and now he is at UMass Amherst. So let us welcome Alan Condron.
So can you all hear me?
Yes.
Okay. Okay. So it's nice to be here. I didn't realize it's a 4.5-hour drive. You know, I didn't quite make it, but and it's also quite nice for me to be talking about this topic, which is sort of my other life, but sort of spent the last 5 years mainly looking at more sort of paleo climate modeling. This is a project that's been sort of sitting on the sideline for a while. It's a project that I started 2003. It was what I went to do my PhD research on, and then sort of ended up going off to MIT and Woods Hole, and then ended up going to paleo modeling, and this was sort of shelved for a little while. So it's, this is the first time I've actually talked about it for a while, so I'm quite excited. I mean, recently had a paper come out, and I'll talk about that. There's a paper in Geosciences, which we're quite excited to get published. But the idea behind this work is that in the Atlantic and over the Southern Ocean, a lot of quite small-scale storm systems, cyclones, and they're about sort of, we go through this in more detail, but they're sort of, imagine they're about 400 kilometers in size. So this image over here is a, let's give it a work. So this one is a storm system off of the north coast of Norway. And the three pictures basically sum up the entire talk. Okay, there are storm systems, and they have a tremendous influence on the ocean. You know, as the storm goes past, it mixes up the ocean. Some of these storms are extremely, extremely windy, and they extract heat from the ocean. And what I'm going to show you is the sort of cumulative influence of these storms going over can actually have an impact on the sort of large-scale ocean circulation in the underneath the storms and in the North Atlantic. And although in this talk I mainly focused just on Atlantic Ocean, you know, the work we've done in the North Atlantic, what we're sort of aiming towards now is looking globally. But for today, anyway, I'm just going to talk about North Atlantic. So there's these mesoscale or mesoscale, depending on where you were born. If you're born in England, we say scale weather systems. And when we define mesoscale, we mean a storm system that's less than 1,000 kilometers in diameter. Okay, and like I just said, they extract a lot of heat from the ocean. There are a lot of these, okay, and I'll tell you exactly roughly how many there are. The key kind of point is that I'm going to make is that they're not actually simulated by climate models or reanalysis data such as NCEP or the ECMWF data sets, say ERA 40, ERA interim. And the reason for that is that these data sets are just too coarse in resolution. They can't capture these small scales, okay? What I'll talk about though is that, interestingly, these storm systems, although they're not in climate models, they occur over regions of the ocean that actually have quite an important influence on driving the large-scale climate system. We'll talk about how they potentially can change things like deep convection in the ocean, which is water sinking to depth, and that's a process that actually controls things like North Atlantic deep water formation and potentially the strength of the Meridional overturning. So they're small, they're not in climate models, but they're in climatically important regions. So what are we interested in knowing? You know, and one of those things is what fraction of these storms are actually missing from models, and also how much air-sea heat fluxes and momentum are we missing by not including those storms in climate models? And does that actually matter if these storms are in there or not? Do these storms actually have any influence on ocean circulation? Okay. That's what we're going to look at. So here's some history about these storm systems. They have sort of variety of different names. Sometimes they're described as Arctic hurricanes. Polar lows is another example. We call them sort of mesoscale cyclones. People may just call them mesocyclones. But here we have an image, satellite image, to the coast of Norway here. And this is the same, this is a storm system here. It's about 400 kilometers across. And the sort of history behind these storms is that sailors and fishermen, they would go out and use their boats, and they wouldn't have, they have a weather chart, and they take a weather chart with them. They'd set out and they'd look at the weather chart and they'd think, oh yeah, it looks like quite a nice day out in the ocean. We'll just go out in our boat. But they would get out into the middle of the ocean, and what they would encounter is not a nice day, but actually a storm system that, quite a small scale storm system, a storm system that wasn't on the weather chart. It wasn't captured, or there was no data fed into the weather chart to include this storm system. It was missed basically from the weather chart. And what they found is not only were they sort of quite small, but some of them were extremely windy. They're quite intense systems. They're gale force to hurricane force wind speeds. Okay. Then, sort of in the 1960s, satellites were put up, polar orbiting satellites. These images came back of the North Atlantic, and what we saw on these images was absolutely thousands of these small-scale storm systems. Okay, and the estimates typically range from about the northeast Atlantic, about 3,000, 3,500 storms a year. Over the southern, that's just in the northeast Atlantic, not including Labrador Sea. We don't really know, in fact, how many there are in total. There's not been that much work done in other regions, like the Pacific Ocean or the Labrador Sea, counting these things. Over the Southern Ocean, we think there's roughly about 8,000 or 9,000 a year. So there are loads of them. Okay, and the estimate now is that they make up about 75%, or 3/4 of all storm systems in the sort of subpolar, subarctic, high latitudes. Right. So the question is, how many of these little guys are missing from models and reanalysis data? So a little bit more information, a couple more satellite images. This is 1987, February, in the Barents Sea. So again off the coast of Norway. There's quite a lot of research going just into purely the dynamics of polar lows. I'm not actually an expert in the atmospheric dynamics behind it. Well, what I'm interested in more is the influence of these little guys on the ocean, and then from an ocean modeling perspective, how that influences global and ocean circulation. But some people get quite enthusiastic about them, and this one was called the most beautiful polar low. So that's, some people love these things, so I should say. So the diameter is this one is about 340 kilometers across there. Had a recorded maximum wind speed of 30 meters a second. That's getting up towards sort of hurricane force winds. It's extremely windy. Another example is this guy, which is February 1984, and the Norwegian Sea, Iceland just there. It's roughly about the same size, 500 kilometers across. Maximum wind speed of 35 meters a second. The reason they know these wind speeds is that there were some quite daring people that flew planes through these storms. Not really my cup of tea, but probably quite bumpy. Anyway, so they're small. They're typically about 100 to 500 kilometers in scale. They have a sort of modal size or mean size around about 200 kilometers across. They're very short-lived, so they only live somewhere between 3 hours to about 2 days. So the fact that they're small, they're short-lived, it means that they're not actually captured by a lot of meteorological weather stations or satellite data, and that's the reason I'll show you that they don't end up going into reanalysis products such as ENSEF or ERA 40, for example. They're maritime features, so they form over the ocean, and they're typically forming a cold air outbreak where cold air moves off the land, for example, over relatively warm water in the North Atlantic, and you get a barometric instability that sort of generates a mesocyclone. There's a lot more detail that could be said about their formation mechanisms, but I'm not really going to concentrate on that today. We're going to be looking at the influence of these guys on the ocean. And they range, they're not all windy, they're not all like hurricane force. Some of them are quite minor in intensity. They do sort of, so they range in sort of being like moderately windy to extremely windy. If they get to be over 15 meters a second, then they get to be called polar lows, so they get a whole new name. So polar lows are a sort of subcategory of quite windy mesocyclones.
Do they have warm cores?
What's that?
Do they have warm cores?
There's a mix. Some of them have warm and some of them cold. Yeah. So the size distribution essentially looks like that. There's not much data actually about this. This is a 2-year satellite climatology that was compiled by Julia Howard back in 1999. And it's compiled by looking at satellite images such as these guys for 2 years, from 93 to 95, essentially measuring the size of these storm systems, and then looking at the distribution. So most of them are around about sort of 100 to 200 kilometers in diameter. And the big question is, for my research, are they climatically significant? So if you take the work of Harold et al. In 1999, and you spatially, this is not probably a bit hard to see, if you plot that up, so this was a data set that was compiled for the Northeast Atlantic. If you plot that data set up, you see this bullseye of intensity. So this is where most storm systems are occurring, and it's right over the Nordic Seas. And if you know anything about sort of what drives large-scale ocean circulation, such as the thermohaline circulation, the processes such as deep water formation, what goes on in the Nordic Seas, which is, so the Nordic Seas is the Norwegian, Greenland, and Icelandic seas here. And what we believe that what goes on in this region in terms of water, the cooling of water, it's sinking and then returning south at depth. We believe that that process is, strongly regulates the strength of the Meridional overturning circulation, thermohaline circulation. So this was the sort of motivation when we originally started this project, was that we had this data set, and it suggested that lots of these storms were occurring over regions of the ocean that that drive large-scale circulation, ocean circulation. And looking outside of the Nordic Seas, there's also quite a lot of these systems in the Omega Sea, which is down here, and then in the Labrador Sea, not really shown on this plot because it was done just for the Northeast Atlantic. But there's also a lot of these storm systems in the Labrador Sea, and again, that's another sort of hotspot for potentially for driving large-scale circulation climate. And then you see a similar pattern in the southern hemisphere. I don't really have a plot of this, but the Amundsen and Weddell Sea and the Bellinghausen Sea are also the Ross Sea, all these places there. Other places where we think that the sinking of water from the surface to depth has an impact on large-scale circulation and climate. And then another sort of further motivation for this work was that in 2010, Matthias Zhang and his colleague, von Storch, came up with this analysis that showed that in the future, conditions favorable for polar lows or mesocyclones would actually diminish as the climate warmed. And they, in their paper that they had published in Nature, they said, as a result of that, you would be losing the sort of forcing effects of these storm systems over the Atlantic, and they sort of went on to hypothesize that maybe that would actually reduce deep convection, the sinking of water in the Nordic Seas, and would actually weaken the MOC. That's quite speculative, but we're actually working with Matthias Zhang now, and we have a proposal pending that's actually aiming to look at whether this statement is true. I don't have an answer for that right now. But what we're getting at here, though, is that they appear to form over quite important regions in the ocean that drive large-scale climate. So thinking about mesoscale atmospheric features, this example isn't for use of cyclones. This is a type of feature that forms called a tip jet, and it's a very intense, so it's mesoscale again, so it's quite small. It's a very intense wind that basically forms off the southern tip of Greenland. Okay, and it sort of builds towards the idea that mesoscale storm systems or features in the atmosphere can influence ocean circulation. So this it's called this tip jet off the Cape Farewell can generate winds up to 50 meters a second. I mean, that's phenomenally windy, and you wouldn't want to be in a boat off of the coast here when a tip jet was happening. But rather like what I'll show you for the mesocyclones is these features are small and they're not actually resolved in climate models. But this work that Bob Pickard and his colleagues from Woods Hole did, which they published in Nature, was that they simulated an idealized model, where they simulated a sequence of tip jet forcing, so a sequence of extremely small-scale wind events at the tip of Greenland here, over the Erminger Sea, and they found that if they applied these 14 events, and they applied some sort of hypothetical sort of heat fluxes associated with that, they found that in a model they could generate a deep mix layer. And as modelers, we tend to think of a deep mix layer in the ocean as evidence that deep convection is occurring. Deep convection is, if you're not quite sure, it's when the water is sort of essentially sinking from the surface. So it's made dense by, for example, from cooling. So if you had a surface piece of ocean and you cooled it, it would become more dense and it would sink to the bottom. Okay, and then this convection process is what's thought to drive, again, large scale ocean circulation. But they find a mixed layer depth of about 2,000 meters, which they take to be evidence of deep convection. So convection all the way from the surface down to 2,000 meters depth in the ocean. And they believe this is this idealized model. They take this to be quite strong evidence that mesoscale systems, in this case tip jets, can have an influence on the ocean circulation. So the question, this leads then to another question is, well, that's quite cool, that's quite exciting. So now we've established that mesoscale features can influence ocean circulation. Does this also apply for mesoscale cyclones? The difference between tip jets and mesoscale cyclones, although mesoscale cyclones are extremely windy and small scale, so that's two things they have in common, the mesoscale cyclones aren't always occurring in the same region, they're much more transient, moving across the Labrador Sea, Nordic Seas, and not in the same place very long. So a bit more of a sort of primer is thinking about mesoscale cyclones in numerical models. And like I said before, the grid resolution of essentially all of the numerical models, the climate prediction models that you read about, they're all at a resolution that's too coarse, which means the grid boxes, grid cells, essentially spaced too far apart to accurately resolve mesoscale cyclones. And this is the case for the latest IPCC CMIP5 models, and they're typically at a resolution of about a degree. And this also applies to reanalysis data sets, which are very frequently used in atmospheric modeling and also used to drive ocean models. Again, they're about a resolution of a degree. A resolution that's too coarse, I'll show you, it's too coarse to capture mesoscale cyclones.
So, yeah, this question.
Yeah.
So if we look at, say, something like the CFXR, the climate forecasting system reanalysis, which actually has about 40 kilometers, are they capturing some?
Yeah, we haven't looked, but well, we know that from work that colleagues have done, as you increase the resolution, you do start to capture more of these features. It's not only a case of resolution; it's also a case of having data to actually feed into the reanalysis.
Yeah, they do actually have satellite data.
No, of course, So
we didn't have a chance to talk about it because about the work being done here. So, but Alan came late, but I wanted to tell him about the work which is being done here. Let's see it. Yeah, go ahead.
But no, I'll show you. What I'm going to show you actually through this talk is, I'll show you in a minute, is what sort of percentage of these storms you can hope to capture at about a degree resolution. Okay. So this, if you took, so this is an example of sort of observations compared to 1 degree reanalysis data. This is UCMWF, some 6-hourly data that's gridded about 1 degree resolution. And so this is one of our storm systems. This is a mesoscale cyclone, sorry, in the Norwegian Sea in 1984. It's about 400 kilometers across, this one. And like I was saying, people actually do fly planes through these things to see what's going on inside. And the wind speeds recorded in this system here, so the red box roughly sort of corresponds to that area. The wind speeds were approaching sort of 30 meters a second, so getting close to hurricane force. If you look at the reanalysis data, the closest available 6-hourly reanalysis data, that circle is where the storm should be, and what you see, well, you don't see a mesoscale cyclone there. There's no significant evidence of this system in the reanalysis data at 1 degree. What you see is just the sort of large-scale background fields. So whereas the wind speeds recorded by the aircraft were close to hurricane force, the reanalysis data is recording a maximum in that circle of about 17 meters a second. So it's just half what it really should be.
What is the red box?
What's it? Sorry?
What is the size of the red box?
The size of this guy, that's about 400 kilometers across there. Yeah. And you can say the wind speed is massively underrepresented, and you can also calculate, so when they flew their plane through here, they also calculated latent and sensible heat fluxes. And they were recording latent and sensible heat fluxes individually of about over 500 watts per meter squared, and that's phenomenal amounts of heat coming, essentially it's heat coming out of the ocean into the atmosphere, which is having a cooling effect on the ocean. I don't have it shown here, but if you were to plot the reanalysis at the same time, you should see a maximum of about 150, 160. So 4 times less than what it should be for latent heat, and about 4 times less for sensible heat. So reanalysis data set, and this applies not just to reanalysis, but to climate models as well. We assume 1 degree is that they're not windy enough and the heat fluxes aren't large enough. And that's the sort of cartoon schematic of what we think is going on, right? And it's a bit like what I was saying about if you were to go out from the coast in a boat, believing what you were going to encounter would be a nice day. But in reality, so this is what you might have, your reanalysis might say is going on. So that's sort of this scenario. But when you actually showed up, what you encountered was a big storm, and what you actually encountered was this guy. You might not have been prepared for that, but the heat flux, the wind speeds, is the momentum, and the heat fluxes are much larger. And this cartoon was drawn with the idea in mind that the continual, and I'll talk about this later, is the continual passage of these storms would weaken the vertical stratification and can potentially trigger isolated deep convection in the ocean. We'll get to that. So the way we worked out roughly what percentage of these storm systems were resolved, and this is work I started doing for my PhD a long time ago, and this seemed to take absolutely forever to do. And looking back on it, I have no idea why it took so long. But essentially all we did was we compared the position of storms in this 2-year satellite data set to storm systems in the closest sort of 6-hourly reanalysis from the same time period. So we used a cyclone tracking system to try and locate where these mesoscale vortices would be showing up in the reanalysis data. And when they overlapped, like this guy, then we said that the reanalysis was not necessarily capturing the entire structure, but at least it had a signature in the right place. And we went on to look at roughly what sort of size the mesocyclone had to be captured. And what we found, so this is again is for about 1 degree error of 40, we found that storm systems larger than about 400 or 500 kilometers in diameter were pretty routinely captured. And there's also a much easier way to actually come up with this plot. You don't have to use a cyclic tracking algorithm, what you can actually do is work on the fact that you roughly need about 4 to 8 grid points to resolve these features. So after a lot of hard work doing this, we could have probably done it in about half an hour on the back of an envelope. But we didn't know, well, I didn't know that at the time. Being a PhD student, you have to do these things. So anyway, so roughly about 3/4 of these storm systems we believed were resolved above when they were about 500 kilometers in diameter or more. And they got smaller and smaller, the fraction of them captured by the reanalysis got less and less. So when you got down to sort of 20, when you got down to sizes of 100 to 200, which is kind of like getting where the modal size of these guys, which is obviously where most of these storm systems are that size, you're only capturing about 20% of them in error of 40. So that was year one of my PhD, producing that. And then we thought, right, let's do some work. And the aim then was to say, right, let's think of a way to try and simulate these or parameterize these storms into the reanalysis data set. And the reason for doing that was that we wanted to put these storms into our reanalysis and then run a climate model that had mesocyclones in the forcing. And the way we came up with to do this was we took a Rankine vortex, like this guy. Essentially, it's this spinning disk of, we sort of think of it as spinning disks of wind, basically, where the wind speed was increasing linearly to R, which was the sort of radius of the storm system, and then out from that was sort of decaying as 1 over the radius. Okay? And what we did was every time we thought there should have been a storm system, we went in and just skip that one. We went and inserted one of these guys into the reanalysis field. So this is the one I showed you earlier. This is this guy. Okay. And then we put in our Rankine vortex of the correct size. And we were quite excited by this because what we did was we managed to produce wind speeds, or parameterize in wind speeds that were getting to be close to the ones that were observed by the aircraft. So that was great, we thought. We had successfully parameterized mesoscale cyclones. Maybe we have. We're still using this technique today, actually. And another example 2, is this another sort of time period. I think this was in '87. Again, it was a storm system where, this is probably quite hard to see, but it's a cyclone that's in here. On the northern edge, there was wind speeds of up to about 30 meters a second. Again, in the reanalysis, we didn't see any evidence of this system. But once we put our Rankine vortex in, we were quite excited that we managed to create a storm system that looked quite like the observations. And there's just, you can look at these examples for hours. This is reanalysis versus quick scat, and then this is a cyclone parameterized in here, which is supposed to sort of represent this guy. Okay, so we think that these Rankine vortices are quite a good way to simulate mesoscale cyclones. And you can go on and look at that. We did some power spectra. I won't really talk about this. This was in our nature paper. We did some power spectra work to confirm that putting these cyclones in, and we only put cyclones in that were less than 500 kilometers because we believed that at this resolution, above 500 kilometers, the energy was already correct. When we put them in, we created a sort of power spectra that agreed much more closely with observations of what the power and that energy should be like in the atmosphere. So we were quite excited about that. So then we thought, right, when I was doing this originally, PhD year 3, because in the UK it's quite short. You go, all right, you only got 3 years to do this, and then they kick you out. So it's tough schooling. The final thing we did was we ran this 2-year simulation. Essentially what we did was that the simulation that had vortices sort of parameterized into the forcing for 2 years, which is also what we call this our pilot study now.
It is a question. So,
yeah.
What sort of intensity spectrum do you put in? Because you only showed the number density chart, but how intense are the
Yeah, so that's probably one of the things that's quite poorly done actually in this work. So when we have a relationship between size of the cyclone and its maximum wind speed. And it's rather crudely based on about 30 mesoscale cyclones, of which there is quite a good quick scan towards aircraft observations. Ended up plotting up a sort of a size versus wind speed, putting a regression through that. And was actually, I don't show that. I can show you later though, but we're still using that. Ultimately, it means that the bigger storm systems are windier. But that, so I think, is probably one of the worst aspects of this work, because I think it's okay, but it could be better. So we ended up parameterizing about 2,500 storm systems into our forcing each year over the Northeast Atlantic. Okay, so well, this is a global simulation, but we only had data for the Northeast Atlantic, so we only put mesocyclones in over the Northeast Atlantic. All right, we put them in exactly where a satellite data set told us that these systems should be. That's how we got the size of these cyclones as well. And then we used bulk flux algorithms to calculate what the heat loss and the wind stress would be underneath these mesoscale storms. Right? And it was quite a crude simulation looking back at it now. The model we used was, I mean, okay, it wasn't, I guess it wasn't that bad. It was about ½ a degree in the North Atlantic, but outside of that it was up to about 2 degrees. This contrasts now what I'll show you in a minute, where our ocean model actually is a 1/6 degree globally. But what we did was we have 2 simulations. This is the crux of it, really. One of them you just force with error 40 for 2 years, and the other one you force with error 40 that has these storm systems parameterized in as Rankine vortices. Okay. And then you compare the 2. It's that simple, right? But this rather bad plot that we made, what we found was after a certain amount of time, in a very short time, was that the water in the Greenland Sea was becoming cooler at depth at about 2,000 meters. Right? This is sort of the big finding that we made from this paper. You could see that when it was cooling, it was linked to what was going on in the surface heat flux. These little spikes here, they were lining up with individual storms that we'd parameterized in to the forcing. So this is cooling at depth, and this is essentially it's mesocyclones going across the Greenland Sea. And every time we saw one of these features, we saw this or at least when we saw a big sort of spike in heat fluxes, we would see these sort of periods of cooling in the deep ocean. And we took that to mean that what these storm systems were doing, they were perhaps, we believe that they were triggering sort of isolated patches of deep convection. They were essentially making water at the surface dense enough to sink to depth. And this process, again, that is one of the processes that's thought to control large-scale circulations. Sinking of water in the, convecting water in the Greenland Sea is linked to North Atlantic deep water formation, which is then linked to potentially is then linked to like MOC or thermohaline strength. So we thought we were seeing, I think we still think we're seeing was isolated episodes of convection occurring in the Greenland Sea, triggered by further mesoscale cyclones. And then we thought, right, well, then there was a bit of a sort of a hiatus, I guess, really, because then I ended up getting sidetracked into paleoclimate modeling, which is actually what I spend a lot of my time doing now. But getting back in touch with Ian, who was in Radford at University of Norwich, and he was an advisor on my PhD, we thought, wow, let's get back into this mesoscale cyclone stuff and let's do a better job, or at least investigate it more. We thought, right, what are good ways to do this? We said, right, well, let's run it for longer, definitely, because 2 years wasn't very long. And let's use a better ocean model as well, one that's higher resolution, one that's getting towards, it's not any resolving this, but any permitting. It's about a 1/6 of a degree spatially. It's a global model. And it looks, and it's MIT GCM, that's about 18 kilometers grid resolution. It's this guy in the corner. And it's configured on this quite cool cube sphere grid, which I sort of use not only for polar low research, but also for paleoclimate research too. And we did the same sort of thing. We did a control and the perturbation experiment. We did a 21-year simulation with just error 40 and then repeat that, but we have mesocyclones in the forcing. This is a sort of, this is just a control run. This is just to show you how nice the circulation in the ocean looks when you simulate it at a sixth of a degree. So the scale is the velocity, the speed that the water is moving at in the surface of the ocean. There's no mesocyclones, but I just wanted to show it because so when you see brighter colors like white, that's quite fast moving water. So that line up there, that's the Gulf Stream going up here. You see it's quite eddying and it's quite chaotic. Okay, and then over here in the sort of Pacific, if you look hard enough, you can almost sort of see these Calvin-Rossby waves going across the ocean. This is the Agulhas or Guaylas current coming over here, just shedding eddies around the tip of Cape of Good Hope. These are quite interesting, actually. Sort of not a side point to this talk really, but there's been a lot of interest in these warm, salty eddies carrying water all the way up into the North Atlantic, and this is now sort of a hot topic of what drives overturning of circulation. But so this is the model. And what else should I say? Oh, this is the sea ice. The white is the sea ice of the model. And the blue around the edges of the sea ice is observations. So we were just trying to gauge how well it did compared to observations. But we like it. We think it's not a bad model. Sea ice in Antarctica needs a bit of work, but it's okay. So we took some snapshots of what happens to the ocean when these storms go by. If you saw, this is a control, so no mesocyclones. This is just a one instantaneous snapshot, and this is the velocity of the ocean. So it's how fast the surface of the ocean is moving. And then this one is one that has a mesocyclone going across the Nordic Seas here. This is the little dot here. When you do the difference between them, you can see that these storms are having an instantaneous impact on the surface of the ocean. They're increasing the surface velocity, in this case by about up to about 0.3 meters a second. But they're leaving these sort of signatures in the ocean, almost like this sort of stirring effect, if you like, on the surface. And then there's quite a lot on this this plot here, but this is some of the main results from the Nature Geoscience paper that we had come out. And the sort of takeaway message here is that when you put, if you don't get anything from this slide, there's probably way too much information on it, but when you put mesocyclones into your model simulations, you increase, rather like our 2-year pilot study, you increase deep convection, the frequency of deep convection, and the depth of deep convection, and even the area that deep convection occurs over in the Nordic Seas in general. And you can see that when you do the difference sort of in deep convection between the two different regions, between the two simulations, you can get isolated patches of deep convection down to sort of 1,000, 1,500 meters. It's deep, okay? Essentially it's evidence that these storm systems can make water at the surface sink all the way to depth. And the average change in deep convection between the simulations is getting on to be about 100 to 200 meters, okay? So that's the first thing. One is that mesocyclones appear to be triggering deep convection in the Nordic Seas. Second thing is that if you look at the dense waters, this is deep water that's flowing over the Denmark Strait. So that's Denmark Strait is the strait between Iceland and Greenland. Okay, and the interest in the Denmark Strait is that water flowing over there is thought to be a key component of North Atlantic deep water formation. So we were interested in seeing if all this additional convection in the Nordic Seas would actually lead to an increase in deep water overflowing Denmark Strait. And yes, it does. Roughly only about 3%. So what you see is this is the difference between the two. Okay, and you can see that over time. So this is more water flowing south and this is less. You see that eventually over time we do start to see more deep water overflow. The question becomes, if you were to run this simulation longer, would that number change? But putting 3% into a sort of climatic context really is the sort of next step for this work. Okay, but we are seeing more deep water overflowing, so more convection, more deep water going over the Denmark Strait. The third thing is the rotation strength of the subpolar gyre in the this is a cyclonic spinning gyre. So the bottom part of the gyre is essentially the Gulf Stream, the piece on the going down the Labrador coast, that's the Labrador current, and then you have the Ermingo current going around the top. So that's sort of it's the components of your gyre, if you like. What we found was that by simulating mesoscale cyclones, that we could increase the sort of rotation strength of the gyre. Okay, in this case, by about 0.8 of a spur drop, or about 6 or 7%. So now we have convection, more deep water, more faster rotating subpolar gyre. And the final thing that we sort of came up with, we found, was that we find some evidence of more heat being transported northwards in the North Atlantic. Okay, so this is essentially suggesting that including mesocyclones in your simulations will increase the transport of heat more towards Europe, essentially, right? And we find that we have short-term variations in heat transport of about 5 to 7%, okay, of the sort of the mean and northward heat transport. Having mesoscale cyclones increases heat transport in about sort of 3/4 or 70% of the months. And really that's sort of it, that's where we are. So what did we find from all that? We found that, yeah, mesoscale cyclones, they extract a lot of heat from the ocean. They're not really captured especially well by models or reanalysis data, okay? We found that simulating them as Rankine vortices does quite a nice job capturing the small scale structure of these systems. And when we put them into our model, we find that we get deeper and more frequent convection in Nordic Seas, increase in dense water, and sort of a spin up of the subpolar gyre. And these are all sort of components that essentially drive large scale circulation. So the sort of ongoing step from this project is based on a sort of proposal that we have pending, is to more accurately sort of quantify sort of how significant those changes are, for example, in terms of climate, but also to put mesoscale cyclones in not just over the northeast Atlantic, which is what we've been doing in these simulations, but it's to go now global with this and to have them in the Labrador Sea and have them over the Southern Ocean. As I said in the first one of the first slides, there's about 8,000 of these over the Southern Ocean each year. Okay, and there's quite a lot of interest now in what the role of the Southern Ocean, the winds in that region, and the sort of the upwelling of deep waters. So the focus of this sort of ongoing work is to go global with this parameterization, with a focus on the Southern Ocean, deep water formation. Okay. I think for my final slide, which is the Titanic sailing into an iceberg, but this is so this is my other life, which is paleoclimate research. And I just wanted to say this because I haven't been down here before. So if you're wondering what else I do with my time, I'm not doing polar lows. Is I'm actually in the process of developing quite a sophisticated iceberg model for MIT GCM to simulate the carving of icebergs off of Greenland, for example, or Heinrich events in the past, and to try and get a better handle on how sensitive overturning circulation is to a freshwater discharge from glaciers. Right? So that's my other hobby. Maybe something to do with the Titanic. Anyway, all right, that's the end. So thank you.
Let us see if there are any questions. Yes, Chris?
So 1912 now counts as paleo?
It's true, I guess it depends on your definition.
Actually, I had a real question.
Oh, did you?
So,
Okay.
you had figures for the percent change.
So,
in,
can you please repeat the question for the
Oh,
audience?
yeah. Oh,
yeah.
Yeah.
Right. Yeah. So you have figures for the increase in the subpolar gyre circulation and the heat flux, which presumably is due to an increase in the overturning circulation. Do you have like a number for the strength of the overturning circulation?
Yeah, oh, so do you want me to so Chris's question is, I think essentially is, what is the change in the overturning definition, right? And yes, we did calculate it, and it's not actually statistically significant at this point.
But it gives you a statistically significant increase in heat flux.
In heat flux, yeah, but at 55 mil. So we were interested in calculating MOC at 26, 25 to be consistent with things like rapid growth. And at that solid latitude, we didn't see a statistically significant change. I mean, you know, but what we find though, and we think we're seeing here is the response, you know, is it takes a while to see. And it begs the question whether 20 years is long to see the cumulative impact of these things. And I believe this is part of the motivation for this proposal, is that if they were more extensive, you know, in our model, if they weren't just over the northeastern ones, but they were Labrador Sea globally, you know, we would expect the impact to be larger on the ocean. You know, and if you ran it, say, for 50 years or more, maybe you would start to see more of a significant change. Right. Yeah.
Thank you.
Yes, actually two. One for the atmosphere and another for the ocean. For the atmosphere, well, if we do the climatology of all scale cyclones over that area, how much in percentage will the mesoscale cyclones take from the total storms?
So are you asking what percentage of total storms are mesoscale?
Yes, over
Yeah.
the region.
So I think we roughly estimate that to be about half to 3/4.
Up to 3/4.
Yeah.
Okay. So
Now that I think
the question might be not so relevant, but why so? Why the cyclones has such small scale? Usually in the
oh, why there's so many?
Right. Right.
No, I don't have an answer for why there are so many of them. I think it's not just how many there are, but which ones. I think there's a lot of work still to be done on which ones are actually important though for the ocean, because although there's, you know, you can look on a satellite image and you can see a lot of these are examples of quite extreme ones, but you can sort of pick a satellite image any day in the North Atlantic and you can probably find a little cyclone-looking feature in the cloud. You know, whether though that, if you went to that location, whether that would actually have a significant sort of, you know, a strong wind underneath it. So although we find something like 3,000 or 4,000 of these in the Northeast Atlantic, I think what we should be doing more is looking at what percentage of those are even windy, or, you know, are strong enough to be really considered important.
Okay, about the ocean side,
Yeah.
You're talking about the impact of the large-scale ocean circulation. Was that circulation in more general sense, like the North Atlantic currents, or some other large-scale currents you're talking about, or something else local?
Yeah. So the question here is, I think, what is sort of impact more locally? Is that what you're thinking on the
Well,
ocean?
I'm wondering which part of large ocean
Yeah.
ocean circulation you're talking about.
Right. Okay. So let me see. Yeah, that's right. I don't have a plot. That's kind of embarrassing. What we're talking about, one of the main things is deep water flowing. So Denmark Strait is here. And so we're looking at the water at depth that's flowing down here, which essentially is part of the deep water boundary current, North Atlantic deep water. We did look at things like Norwegian coastal current, East Icelandic current. And you do see changes in those, yeah. But again, they weren't actually statistically significant at this point. So they do.
The polar giant, you could show the changes in the polar giant.
Yeah, then we do have a, if you do you can do it, we did a stream function very similar to the subpolar gyre. We did that for the Greenland sea gyre. And then, I forget what the result of that was, but we do see a spin up of the Greenland sea gyre as well. Yeah, I can't remember the percentage off the top of my head.
So, Ivy, did you have a question?
Yeah, so the IPCC model, I remember that the model already simulates the MOC very well. So how much do you think, including the mesoscale storm, can improve?
Yeah, what's the improvement?
Can you please?
Yeah, so the question is, by simulating mesoscale cyclones, what would be the improvement in the overturning? I don't think we don't have an answer for that. I mean, my understanding now is that most models tend to have a slightly weaker overturning than perhaps observations would suggest. We would expect, I think, an intensification of the overturning.
So
By how much? We can't quantify that yet. We're running out of time.
Yes. Well, first of all, great to see another person from West of Wales. Glad. My question is on the subpolar gyre, how it's enhanced. Is it more of a thermodynamic, or is it a question of imparting the impart momentum, which is which?
Yeah, we haven't actually looked at the partitioning of the fluxes.
Right.
Because I mean, you have they're both you have the momentum and you have the heat fluxes. We haven't actually sort of separated out the contribution of each one of those. I mean, a way to do that, I guess, would be you could artificially impose. You could fix the heat fluxes and then increase them. So you have a simulation, for example, where you kept the heat fluxes as the error 40 suggests, just have the wind increase the wind forcing. I think that's my understanding. So we need to do another model simulation to do that.
Yes, Charlie. Yeah.
I have a question. These 3,000 or 3,500 mesocyclones a year, that means there's 10 of them a day. And
Right, yeah, that's a good
it doesn't
point.
look like there's enough room to stick them all in. So
Yeah, so some of them are, like I was saying, some of them are just almost like wisps of sort of cyclonic looking cloud, if you like. And I think that is, I mean, it gets back to, whether those little wisps are actually, if you were standing underneath that, whether you would feel any increase of wind, for example. I mean, that number could potentially be an overestimation. Yeah, right, I mean, 10 a day is it's a lot, but you could go on a satellite image, probably, bring one up now, and you could probably easily find, I'd say you could easily find comma-shaped clouds.
One more question, please.
So this is actually related to Kamazima's question about the spin up, in that you said that there's some of them are warm core and some of them are cold core. And so presumably some of them are cyclones and some of them are anticyclones.
Sort of like high pressure.
Yeah. I mean, it's just you change the sign. Of the
Let's say you have like a meso high.
Yeah.
A meso low. We haven't looked. We haven't looked at like mesoscale high pressures.
So these are all low, so they all have the same sense of torque on,
on
the
yeah.
ocean.
So
So that would definitely be a net momentum.
Yeah, they're all cyclonic.
Or net vorticity.
Yeah, I'm not sure if there's been much research done on mesoscale high pressures.
But if you treated them as just eddy, normally with eddy, and then the large scale as kind of mean, that would go on to destroy them. So if you have a mean field and then you put in eddy, kind of, it messes up, it destroys them. I think it's more thermodynamic.
So that discussion we can have later. So let us thank Alan for such a nice talk.
Oh, I mean, think about